After our brief exploration of discrete random phenomena, which was basically designed to just start us thinking about randomness, which is something that so far in the calculus course, of course, we haven't done, we want to get back to continuous random phenomena on one hand because continuous stuff is what calculus is about, but on the other hand also because when we're looking at a continuum of outcomes, that's really when we talk about scientific measurements. Scientific measurements return real numbers. Real numbers are part of a continuum of numbers. They are no longer really viewed as discrete entities, even though we measure single numbers. And, well, measurements return real numbers, at least in principle. I mean, technically, we could say, yeah, quantum mechanics and all those things, everything is discrete. But basically, working with an extremely fine, discrete scale is so much more trouble than it's worth because the models would get so complicated and the numbers would get so big that continuous modeling will remain with us, probably will remain with humanity until the end of science or so. And so basically that means we really have to make friends with this idea that we no longer have discrete outcomes, and one of the first consequences is that when you're working with a continuum of outcomes, then we cannot simply assign probability to individual outcomes, because there is a way to assign probabilities to even an infinite sequence of discrete outcomes, but, and there are some very good abstract reasons behind that, the continuum of real numbers, the interval from negative infinity to infinity, even the interval from 0 to 1, cannot be represented as a sequence. There is a certain way to determine that the interval from 0 to 1 contains more numbers than the natural numbers. So consequently, what's happening is that we're going to be interested not in the probability of individual outcomes, but we will be interested in the probability that outcomes are in certain sets. And in some ways that makes sense, because when we are measuring something, then we can be interested in the probability that a measurement is between two numbers, say 3 and 5. We are, as long as at least we're doing mathematics, we're not going to measure the sample space explicitly, and that is something that will be come back a few times throughout this presentation and also throughout the rest, because the sample space will give us the interpretation of the computations. Alright, so what's the definition? Basically, a random variable will be called continuous if and only if its set of possible values is an interval on the real line. So note that we're no longer talking about the sample space or anything like that. We're just talking about the numbers that the experiment, that the random variable returns to us, and we're just going to analyze those numbers. So we could think of these random variables as functions without arguments. That is something that people in computer science are quite familiar with. For those of us who don't have a computer science background, we could think of these things as functions such as the rand function in a spreadsheet. Let me grab the right example here. The rand function in a spreadsheet just returns a random number with a certain distribution, and it's going to be a uniform distribution between 0 and 1, and we will also explain in this course what that means. But the rand function is just a function that is called rand, and it doesn't have an argument inside. It's got a set of empty parentheses where typically we would say of x or so. And this is a function that whenever it's queried, query just means that whenever something changes here in the spreadsheet, the function will return a new value. So whenever that function is queried, it returns a random number. And so in some ways, the function rand then, at least in principle, is similar to a measurement of a physical quantity, because if you will, a measurement of a physical quantity also doesn't have an argument, right? You take the measurement, you get a number, but there wasn't anything where you plugged a number into another function or into the experiment or so in order to get the number that you are measuring. So that, at least in principle, means that physical measurements are also like functions without arguments. Now, in other ways, of course, measurements of physical quantities are quite different from the rand function, because when you measure time, when you measure length, when you measure pressure, when you measure pH value, and so on. We've got to remember that measurements are influenced by randomness, but the measurements are not themselves random. They are influenced by random errors, but if I measure the pH value of a certain solution in a chemistry lab and my first measurement gives me a pH value of, I don't know, 5.7, then if I measure it again, I'm not going to get a pH value of 1 after that, unless I have done something to the solution that I have in the chemistry lab. What I could get, however, is a measurement of 5.71 or so, because there may be random fluctuation in the apparatus, or the apparatus may only have 2 digits that really are fully reliable, and the rest is influenced by randomness, right? Influenced, not random itself. Okay, so now the question is, as we are looking at situations that return a continuum of numbers, how do we turn that into something that we can analyze? And ultimately, we will even be able to analyze something that is as truly random as the rand function, something that just spits out numbers that are randomly distributed between 0 and 1. Well, when we are making a connection between continuous and discrete scenarios, one of the things that you also often see in a newspaper or in an online article when people present data is a histogram. So let's take a look at the idea of a histogram. And basically, a histogram is just a way to take continuous data and represent the number of outcomes that you have in a certain interval, say here in the interval from -6 to 0, and in the interval from 0 to 6, and with bars represent how many outcomes are in each interval. And so if you're looking at this histogram, you would say these two bars have the same weight, have the same size, and so therefore, if this represents a set of measurements, I have equally many measurements between -6 and 0, and between 0 and 6. Now what I have already done is I have scaled this whole thing in such a way that the total area of the bars, if you measure width times height, the total area is going to be one that is something that we're going to see on the next few slides and panels also. But let's take a look now at this histogram and realize that this is a very crude way to represent data that is distributed over an interval of length 12, right? That just tells you that we're equally likely to get a measurement to the left or to the right of 0. So if I split this data up into 3 intervals of equal size, all of a sudden we see that actually most of the data is likely to cluster around the origin, and very little data is likely to be between 2 and 6 and between -6 and -2. Okay, and so now what I can do with this histogram, I can keep using smaller and smaller bins, and basically what I then get is a better and better picture of how the data is distributed between -6 and 6. Here we're already seeing something that looks like a curve, and if I keep refining this kind of thing, well, this is now not the same kind of presentation as what we did see when we did our integral calculus, but this starts looking very much like a Riemann sum, right? These are rectangles, and if we have enough of these rectangles, and let's just stop the pushing right here, oh well, I might as well just push it all the way out to its extreme. If we use enough rectangles, well then of course my scale on the x-axis is completely smeared out, but what we can see here is that this is basically looking like the area under a curve. And that is really the idea that we're going to use to connect continuous values with probability, because what we can define is that the probability density function of a continuous random variable is a function f, so that for any numbers a smaller or equal than b, we have that the probability that my random variable gives an outcome between a and b is the integral from a to b of this function f of x dx, right? Basically, the idea of a histogram says that the size of the bar tells us how likely we have measurements in the interval that is represented by that bar? Well, as we refine that, we realize that that's basically just area under a curve, and so this becomes a fairly natural idea. And so now, for the rest of the first half of this presentation, we're basically going to look at two things. We're going to look at the mathematical ramifications of the whole thing, and we're going to look then also at how to interpret that. So every so often we also have to come back to this x. So first of all, well, we can see here probability that x is between a and b then is always visualized as this area under whatever our density function is from a to b. And the keyword that is going to accompany us through the rest of our presentations on continuous random variables and through the rest of our statistics module here is that area does represent probability. Okay, so now when is a function a probability density function? A function is a probability density function if and only if the following hold. The function has to be greater or equal than 0 for all real numbers x, and that's because, well, our integrals can't be negative, right? You can't have negative probabilities, so we've got to have that f is greater or equal than 0, and the integral from negative infinity to infinity f of x dx must be equal to 1, and that is because the probability that we get a value in our experiment always has to be 1, has to be 100%. And so basically that means that the generic picture of a probability density function still remains a non-negative function with a total area of 1 underneath the curve. Total area under f is 1. Okay, so I've just told you that if this thing is a probability density function, then 1 and 2 must hold. If these two don't hold, then something goes wrong. Why is it the case that when these two hold, that the function really is a probability density function? Well, that is because the assignment of the probability of some random variable being between a and b, being the integral from a to b f of x dx, that really is a probability function. And that's fairly easy to prove, basically because the function is greater or equal than 0 for all x. All the probabilities are non-negative because the integrals are always over non-negative functions. Because the total integral is 1, the probability of getting a number, to get any number, is 1, and that was always the law that says the probability of the whole sample space, which is that we get a measurement, or the probability of negative infinity to infinity as an interval, which could be sort of a stand-in for the sample space, that has to be equal to 1. And finally, then, the only other law that a probability function has to satisfy is that probability is additive, which basically means that when we've got two disjoint sets, E and F, over which the function can be integrated, well, then the probability of the union of these two sets is the integral of the function over the union of these two sets. Think of the union of two intervals that are disjoint or something like that. And, well, we know that we can split up integrals if the sets are disjoint, so the integral over E union F, f of x dx, is just the integral of E over E of f plus the integral over f of f, and that's nothing but the probability of E plus the probability of f. So that means that this really does work out on the technical side. Now, on the interpretation side, we have to remember that random variables will remain vitally important. Now, first of all, when you look at the definition from the previous panel, basically any function with the properties of a probability density function, of a density function, really is a density function. There is, in fact, an abstract way to just artificially make a random variable that will have this density. But on the other hand, we can only interpret what's going on, what happens in the experiment that is described by a given function, if we know the corresponding random variable. For example, high probability that my password will be emailed to you in the next few minutes. That's a good thing if I'm waiting for a password to sign up for something, or because I want to make a purchase of something or so, and it's actually a useful purchase. However, on the other hand, high probability that I will receive more than a safe dose of radioactivity in the next few minutes, that's a bad thing, right? And yet, the underlying, and these things are then called waiting time density functions, those may be the same for both phenomena, Of course, high probability that you get a password emailed soon. That is something that is just basic customer service. Now, if you are currently in a marked zone of a reactor, then you've got basically the same waiting time distribution, but hopefully you also know about that and will move away from the radiation source very quickly, because typically these kinds of zones are restricted. So what I'm saying here is the same mathematics can describe entirely different phenomena, and that's great for the mathematical side because we'll be able to use the same computations, but the interpretation will be up to the engineer and to the scientist to determine what action has to be taken based on the data that we have, based on the probabilities that we get. Okay, so abstractly, what does the density function do? The density function really gives probability per interval. Take A smaller than B so that A and B are, how we always say in calculus, sufficiently close together. Remember, whenever you take sufficiently short intervals, things become straight lines in calculus. So that's the kind of sufficiently close together that we're talking about. Well, then the probability that our x is between A and B, or as it's also denoted, the probability of the interval AB, would be the integral from A to B of the density function dx. And that integral, if the interval is reasonably short, well, then we know that fx of x is approximately fx of A, and that means that the integral is just the area of a rectangle, and so we just get that the area is base times height, right? And if we solve that for fx of A, that means that fx of A is at least approximately, for B being close to A, the probability of getting an outcome between A and B divided by B minus A, and that is exactly what a density is, right? A density, physically the density in physics is quantity per space, or mass per volume. Yeah, that is quantity per space. And so in this case, that translates to our quantity being probability and our space being a length, so we get probability per length. Now, something that you've just seen on the previous panel is that I didn't worry about whether my interval was open or closed, and that is, for continuous random variables, single points, boundary points don't matter, because the probability that our random variable will be exactly equal to a certain real number, that probability that x is equal to A, is the integral from A to A f of x dx, where we're again integrating our density function, and we know the integral from A to A of anything is 0. And so that means the probability that A is less than or equal x is less than or equal than B is the integral from A to B f of x dx, but that's also equal to the probability of A being less than or equal to x and x being strictly less than B, because the only thing we could add here is the probability that x is equal to B, and that's 0. And then similarly, we could also drop the left endpoint, or we could drop both endpoints from the interval. And that is something that is at first a little bit strange, because when we do take a measurement, we get a number, but we've got to remember that when we take a measurement, we only record the reliable digits, and so when you measure a pH value of 5.75 in a solution in a chemistry lab, you didn't really measure 5.75, you measured 5.75, and there are infinitely many digits behind that second 5 that you really don't know. So you didn't measure an exact number, and then in that sense, still the probability that your random variable is exactly 5.75 remains 0 here. Okay, so the remaining examples now are entirely mathematical. It's completely computational, and that's perfectly fine. We will keep coming back to interpretations as appropriate, because certainly, as I said, the interpretations is what breathes life into the mathematics. But let's right now just verify that we can get on top of the mathematics itself. So for example, if we need to prove that the function f of x being 1/3 e to negative x over 3 for x greater or equal than 0 and 0 otherwise, so 0 for x smaller than 0, we want to prove that that is a probability density function. Well, there are two steps. One step is typically pretty quick, because you just look at the function and you hopefully see that it's the case, and that is, this function is greater or equal than 0. 0 is greater or equal than 0, and exponentials are never negative, so this thing is greater or equal than 0. So typically, The only step we really have to worry about is that we have to compute the integral of the function from negative infinity to infinity of f of x dx. And when we do that here, we realize that when a part of our domain has been cut out, well, then that means because the function is 0 up to 0, where our integral only goes from 0 to infinity, we integrate the function, of course. That's a quick u substitution. U equals negative x over 3. You work out your du dx and everything else, and you realize that the antiderivative is negative e to the negative x over 3, and it's in the boundary 0 to infinity, so we're also using our knowledge of improper integrals here, because that certainly is an improper integral. And what we get is that at infinity, the negative exponential goes to 0, minus the value at 0, which would be minus negative e to the negative 0. And that's, of course, 0 minus negative 1, and that's 1. And because I should model everything that we have to do here correctly, let me also quickly put into the slide that the function is indeed greater or equal than 0. Okay, I'm back. Sorry for the interruption here. Basically then, one more statement, quick sanity check. Yes, f of x is greater or equal than 0 for all x, and that means both properties of a probability density function are satisfied, and that ends this example. Alright, that's not that bad, right? It's just straightforward calculus with integration and improper integrals. Okay, so now let's look at an application where we're interpreting this function a bit. So here we're looking at the probability density function for the waiting time for an email that provides Dr. Absent-Minded his forgotten password. That function is the function that we've just looked at, 1/3 e to the negative x over 3 for x greater or equal than 0 and 0 otherwise. What is the probability of having to wait more than 5 minutes? Well, the probability that our waiting time t, just give it a name, probability that the waiting time is greater than 5 is, of course, the integral from 5 to infinity, because that's the interval that contains all numbers greater than 5, right, of the density function, which, because we're already past the place where the function is 0, it's just the integral from 5 to infinity, 1/3 e to the negative x thirds dx. And now we just do our calculus. We find the antiderivative, so we either do the u substitution again, or we remember what the antiderivative is from the previous panel. It's still negative e to the negative x thirds. This time the bounds are 5 to infinity, because we want to have the probability of this interval. Well, as x goes to infinity, that exponential still goes to 0, and at 5 we get minus negative e to the negative 5/3. So the probability, if you want to give an exact value, if you don't have a calculator, that's e to negative 5/3. Of course, we don't quite know what that number is, and so with a calculator or with a machine, you realize that's about 0.1889, so about 19% or so. So there's a 19% chance of having to wait more than 5 minutes, so maybe the good doctor could go and get himself a cup of coffee or something like that. And, well, that's how we can then interpret probabilities, and waiting times will be an example that we're going to look at quite a few times in our presentations on continuous probability, and that is because the waiting time is connected to the very important engineering concept of time to failure. Basically, anytime you have a device, anytime you buy something, ultimately that thing will break, and determining how long this thing will function helps you to determine how long you have to save, how much time you have to save up to buy a replacement unit, like for a new cell phone or something like that, or how much time you have, what kind of a warranty a company that builds these things can give on the device, and hopefully it'll be a long warranty. Alright, the only other thing we can do computationally at this stage is that somebody might tell us that the function f sub k of x, which is defined to be k over x squared for x greater or equal than 3 and 0 otherwise, that is a probability density function, and we're supposed to find the value of k. And the philosophy behind that will be explained on the final panel right now, let's just take a look at this. Does this function even have a chance to be a probability density function? Yes, it does, because it does return non-negative values. That's the sanity check we always want to do, even if somebody tells us something is a probability density function. And so then, well, the only thing that could go wrong is that the integral may not be 1, but we've got this undetermined parameter k that we can probably adjust in such a way that it works out. So we set 1 equal to the integral of the density function over the whole interval from negative infinity to infinity, and then we get that this is the integral from 3 to infinity of k over x squared, because for x less than 3 we get 0, and so the integral would return 0. We can pull the k out of the integral. The antiderivative of 1 over x squared is negative 1 over x, and we have to take that at 3 and at infinity. Well, that gives us our k times value at the upper bound is 0 minus value at the lower bound, which is negative 1/3. And so that means 1 has to be equal to 1/3 of k. And if you solve that for k, of course you get that k is equal to 3. And well, that's it for this problem, because we were only supposed to find the value of k. We could also now write down that the probability density function actually is f of x being 3 over x squared for x greater or equal than 3 and 0 otherwise. Another way to express what we just did in that example is that basically the function f of x equals 1 over x squared for x greater or equal than 3 and 0 otherwise. Well, that function is not a probability density function itself, because we've just seen that that integral, if you go back to the previous panel, that integral is 1/3, so it violates one of the axioms. But it is greater or equal than 0, and it can be rescaled to become a probability density function. Basically, we just have to multiply it by 3. And the larger idea behind this statement and problems that are phrased that way to say, okay, rescale it so it becomes a probability density function, is that as long as the integral of the function over the whole real line is finite, any non-negative function, remember, yeah, it's got to be non-negative, any non-negative function f can be turned into a probability density function by just multiplying it with the right scaling factor, and that is something that we're going to see in the following, because there will be quite a few interesting functions that, if you will, just have the right shape to describe certain phenomena, but which have a complicated factor in front that assures that the integral is 1, because the function itself just has a really complicated integral. So let's not be surprised as we are investigating further probability density functions that there may be strange factors out front. In probability, typically whatever strange factors are in front of the function, they're just scaling factors to make sure that our function indeed is a probability density function. All right, so that gets us through our first introduction to continuous probability. Basically, the main thing that you want to remember at this stage is that these density functions are greater or equal than 0, and their total integral is 1. Much of what we're going to do, much of what we can assess, can basically deteriorate, if you will, into a quick computation with improper integrals. There's nothing wrong with that, because these computations will give us the results. And then, of course, what we want to do with the results is we want to interpret those, and that's the kind of thing that we might also talk about in class a little bit. Whenever you solve a problem like that, think about that think about the solution in terms of a sanity check. Does this probability make sense? Does it make sense that I've got a 25% chance to wait for my forgotten password to be emailed to me from a certain server? Well, I've made these slides a while ago when certain servers may have just had a hard time responding in time, and so it felt pretty realistic to me. I think response times have improved, but basically it wasn't totally out in left field. It wasn't like I had a 95% chance of waiting forever for my password to be mailed to me in this example. That's the kind of thing that you want to think about as you do probability. You want to take the problem and interpret it in a real-life scenario. Okay, that part of the sermon ends right here. I'll see you in the next presentation. We're now going to look at 3 very widely used probability density functions, and yeah, I'll see you for those. Thanks.